Hey there, and welcome to This Explainer. Today, we're cracking open a fascinating chapter on a universal, everyday problem, keeping messy, chaotic data perfectly organized. I mean, think about it. Whether you're tracking your own personal expenses or just trying to organize a digital address book, you've probably bumped into the absolute frustration of messy data. So how do massive systems handle millions of pieces of information without completely falling apart? Well, we are going to unpack the core concepts of database management straight from this chapter to see exactly how all this invisible architecture works.
You know, the writer Nisarga Jain once noted, "Inconsistency of your mind can damage your memory. Remove the inconsistent data and keep the original one." What's really fascinating here is that managing chaotic data isn't just some philosophical struggle for our human brains. It is a deeply practical, highly technical problem for computers too. Because if a system's data is inconsistent, its digital memory is effectively damaged. And today, we're going to learn the cure.
So here's our quick roadmap from absolute chaos to perfect structure. First, we'll look at the problem with files. Then, we'll enter the database. After that, we'll break down the relational data model. And finally, we'll unlock database keys. Let's dive right in. All right, part 1, the problem with files and manual ledgers.
To really understand why databases are so revolutionary, we kind of have to look at how things used to be done. Let's ground this in a totally relatable example. Picture a typical school office trying to track student attendance. Imagine a teacher manually marking a paper register every morning. If there are 50 students in the class and 26 working days in a month, that teacher is making 1,300 manual entries every single month, and that's just for one class. Imagine the sheer pain of that, not to mention the massive potential for human error. What if a cup of coffee spills on the register? It's a complete nightmare. But here's the kicker. Simply moving this paper ledger to a basic computer spreadsheet doesn't actually solve the core issues.
And that leads us to what we can basically call the villains of early computer file systems. When we just use simple flat files, we face data redundancy, which is literally typing the exact same data in multiple places. And because of that redundancy, we inevitably get data inconsistency. Say a student's address changes in one file, but nobody updates the other one, suddenly the system has no idea which one is actually right. Then there's data isolation, where your files totally refuse to talk to each other. We also run into data dependence, meaning if you change a file's format, you accidentally break the software that's trying to read it. And finally, it is incredibly hard to control access. You can't easily let a teacher edit attendance while blocking them from, say, the official principal records. It's a mess.
Which brings us to part 2. Enter the database. Our data rescue mission.
Okay, so to defeat these data villains, we need a hero, right? That hero is the Database Management System, or DBMS. This software swoops in to completely centralize our data. But it has to start with a plan. That plan is called a database schema. This is the logical architecture of a database. Think of the schema as the ultimate blueprint holding the whole shebang together. It defines the table names, exactly what kind of data is allowed, like strictly saying a phone number can only contain numbers, and how all these different pieces of information relate to one another. It's the skeleton of the system. So how do we actually interact with this awesome structured blueprint? We use a query. A query is simply how we talk to the database. Instead of a human manually scanning 1,300 rows in a spreadsheet, we literally just send a query asking the system to, say, find all students absent on September 1st. And boom, the database does all the heavy lifting, delivering the exact result to us in milliseconds. Moving right along to part 3, the relational data model. Let's look under the hood.
Now we know the DBMS is the software itself, but the relational data model is the specific framework it uses to organize everything behind the scenes. To really appreciate its genius, let's look at one of those villains in action. Here we have an old-school flat file. We've got 2 students, Talim and Ali. Now they're siblings. Notice the major flaw here? We are forced to type out their guardian's name, Himanshu Shah, and his phone number twice. If Himanshu gets a new phone number, someone has to remember to change it in 2 completely different rows. If they miss one, the data is corrupted. This is data redundancy at its absolute worst.
But in a relational database, we totally clean this up. We do it by splitting the information into separate, highly focused tables. Check out this new student table. It strictly isolates just the student data. Notice that very last column? Instead of a bulky guardian name and phone number repeated over and over, we've replaced it with a sleek, shared GUID, a guardian ID. Both Talim and Ali now point to the exact same ID number.
And where does that ID point? Right over to the guardian table.
Himanshu Shah's details, his name, his phone number, his address, are now entered exactly one time in their own dedicated home. Redundancy is totally defeated. Because think about it, if Himanshu moves to a new house, we just update his address one single time in this table. Instantly, both Talim and Ali's school records reflect the correct information because they both reference the single source of truth. It's a total game changer.
We do the exact same thing for attendance. Notice how elegantly this attendance table functions. It doesn't even need to know the student's name or date of birth. It simply uses the attendance date, the status of present or absent, and the student's roll number. That roll number is literally the only hook the database needs to link this single day's attendance right back to the student's full profile.
Now, as you navigate through these tables in the chapter, there's a bit of terminology you should definitely know. You might hear the word tuple. Don't let the technical jargon intimidate you here. A tuple is simply one single row of data in a table representing a real-world entity. So, that specific row containing all of student Atharva Ahuja's details, that one row is a tuple. Simple as that.
We also measure our tables using two specific terms. First up is degree, which is just the number of attributes or columns in a relation. Second is cardinality, which is the number of tuples or rows. The absolute easiest way to remember this? Degree measures the width of our table and cardinality measures the height. And finally, part 4, unlocking database keys. This is the structural glue of the whole operation. Okay, so if everything is separated out into all these different tables, how does the system possibly put it back together? The answer is database keys. Let's compare two types, the candidate key versus the primary key. In any given table, you might actually have several columns with totally unique info, like a guardian's ID is unique, but their phone number might be unique too. Both of these are candidate keys. They're essentially your options. But the database designer must choose one to be the ultimate identifier for that row. And that chosen champion, that becomes the primary key. In our school example, we crowned the Guardian ID as the primary key. Now this is where the real magic happens, the foreign key. A foreign key is basically the bridge. It's an attribute in one table that points directly to the primary key of another table. Remember our attendance table from earlier? It had a column called roll number? Well, that roll number in the attendance table is a foreign key. Its entire job in life is to point back to the roll number primary key over in the student table. This invisible string seamlessly connects the data, instantly matching daily attendance with a full student profile without ever duplicating a single keystroke. It's brilliant.
So, as we wrap up this explainer, I really want to leave you with a thought. Every single time you log into a streaming service and see your beautifully personalized queue, or you check out a shopping cart online, you're interacting with incredibly complex relational data models. Millions of rows, smoothly connected by primary and foreign keys, all working together in absolute milliseconds. It makes you wonder, what invisible relational databases are organizing your daily life right now, holding together all the fragments of your digital identity? It is a fascinating architecture literally running our modern world. And now, you understand exactly how its foundation is built. Thanks so much for joining me today, and keep exploring.